This is Lecture 8A for Calculus 2, Examples of Arc Length Calculations. And now we come to something that I have said is very sad. We have this nice expression which we spent some time deriving. I'll just write it for the arc length function. S of x is some integral from some point x1 to x of 1 plus f prime squared d tau. And it doesn't look that bad. In fact, it looks rather benign. The problem is that there are very few curves that have a closed form solution for these definite integrals. I give an example here of the sinusoidal curve. I think it's given as one of the exercises in I think it's in Stewart, or maybe it's in Thomas' calculus textbook. And you have this very common curve, a sinusoidal curve. So if you set up this arc length function here, you would take first the derivative. So here's f of x. You need f prime of x, which in this case is cosine of x. And in the expression, you have f prime squared. So here you see the cosine squared. And this integral, the square root of 1 plus cosine squared, does not have a closed form solution. The solution must be obtained numerically. There are a few curves that do have closed form solutions, and I've listed them on the next slide. Okay, so the line, a circle, and a parabola all have closed form solutions for the arc length. There's another function, the semicubital parabola, which is y, or f of x, equals a x raised to the 3/2 power. This has a closed form solution. The catenary, which is the hyperbolic cosine, that also has a closed form solution. There are two other curves that we studied in Chapter 10 that have closed form solutions for arc length and arc length function, and those are the logarithmic spiral and a group of curves called cycloids. I'll do a couple examples here for arc length. Let's look at the circumference of a circle. So to find the circumference of a circle, all we need to do is look at the arc length in the first quarter of a circle using the symmetry, and then multiply by 4. So I need a function that describes the arc length, describes the circle in the first quadrant. That's given here. F of x equals the square root of r squared minus x squared, where r is the radius of the circle. Now in the arc length function, we need f prime squared. So first I'll compute f prime. Here's f prime. Then I get f prime squared. Square this, I get x squared over r squared minus x squared. The function that appears under the square root sign is 1 plus f prime squared. So I do all this calculation before I start writing my integral. And now notice that as x approaches r, there's a division by 0. In other words, there's a vertical asymptote occurring at x equal r. This is an improper integral. To handle improper integrals, if you recall from one of the previous lectures, we replace the limit of integration. In this case, we would have been integrating, let me write that out so it's a little clearer here, we would have been integrating from 0 to r of 1 over 1 minus x over r squared dx. And the problem was that when x equals r, we have 1 minus 1 in the denominator. The reason for that is if you look at that first quarter of a circle, this is what we're integrating over from x equals 0 to r. Okay, this is a vertical slope right here, and that's what's causing the problem. So we replace the offending limit with a dummy variable. In this case, I let it be x. It made sense. And I take the limit as x approaches r of this integral. to evaluate this, we can use a change of variable, and I'll finish the problem on the next slide. Of course, we also have to change the limits of integration, and here becomes the problem. L, the total length, is the limit as x approaches r of r times the integral from 0 to x over r, 1 over 1 minus u squared du. Now, the reason that this arc length has a closed form solution is because the integral of 1 over u squared du has a closed form solution, and that is the it's the arc sine of u plus c. We use this result, evaluate it between the limits of 0 and x over r, and we end up with pi r over 2 for the arc length of a quarter circle. Multiply that by 4, we get the circumference of the whole circle, which is 2 pi r, as expected. Here's another example for the arc length and the arc length function for a parabolic path. So if we just let a parabola follow this parabolic path, we'd like to find the total distance followed by the projectile. For example, a projectile that shot up into the air. Let's say we'd neglect air resistance. Just get the simple solution here of x squared minus 9x plus 21, just for example. Okay, so now we need to find the arc length. The arc length is going to go from x1 to x2, and if we want it between specific limits of, say, 4 to 5, those become our limits of integration. 1 minus f prime squared, we have to take the first derivative and then square it. Okay, we'll make a change of variable and let u be 2x minus 9, easy enough, and our integral becomes 1/2 times the integral from minus 1 to 1 of the square root of 1 plus u squared du. The integral of a squared plus u squared du has this closed form solution here. And of course, in our case, a is 1. That simplifies things a little bit. We can use this result, evaluate it at 1 and minus 1, and get the arc length, and this is between 4 and 5. So we had a specific values that we were integrating between. All I'm doing is just sort of walking you through how you would do these different steps. Most of them are fairly elementary. But what I really want to show you with this is the arc length function. Okay, the arc length function is essentially the same integral, but I'm integrating from some beginning point, in this case I'll call it 4, to some arbitrary point x. And this is the arc length function. I have a mistake in here, I'm seeing now, and that is I needed to have a different variable of integration. And I really don't need these limits. Okay, use the same change of variable and basically the same, using the same procedure. And now we have an expression for the arc length function. You'll see here that it really is a function of x. Okay? Looks a little long, but you can see it varies with x, and I could even plot it. If I let x be 4, then that is the length from 4 to 4, which is going to be 0. That's why this is 0 here. But as I move along the curve from 4, and let's go ahead and go to 5 since we have our solution for that, then this curve, the length changes. It's not just a straight line. There's a little bit of a curve here. It's not real pronounced, but that has to do with the functional form for s of x. So this arc length function is indeed a function of x. We can even graph it as we've done here, and it will give us the length along the curve, in this case between x, and then I use the upper limit 5 just to show you that it does make some sort of sense, because if you remember, the length from 4 to 5 was 1.147, and you can see that's what we get here.